Okay, perfect. Thanks so much. So happy Valentine's Day, everyone. I'm Erin Barrett. I'm the CEO of Eigen Innovations. We're a Canadian-based company that focuses on helping our industrial clients maximize the value of their machine vision technologies across their enterprises. Our team consists of software engineers, mechanical engineers, and folks who have extensive know-how in machine learning and AI, but also extensive experience deploying advanced vision solutions within manufacturing. This slide gives you a bit of a view of some of our know-how. We've been deploying machine vision solutions for the better part of 10 years. Over that time, we've experienced a lot of challenges in deploying deep learning applications, as I'm sure you all can relate to. And out of those challenges came a suite of software tools that helped us enable some more advanced analytics and image acquisition. I'll talk a bit about some of those tools and how they helped us go a bit faster to drive even more value for our customers. But before I jump into that, one of the things that makes us unique is we're working with our customers to take vision beyond just detection. So driving process-related insights to prevent defects from happening to begin with. That's been very, very core to what our clients want to be able to do with machine vision. And we're leveraging tools that leverage AI to be able to do that. I think you can probably all relate to this slide. This is really what we have been experiencing over the last, well, since I've been at Eigen over the last 5 years. I would say that this list, what you see here, is most likely the reason why we're seeing adoption at a slower pace than we'd all like within industrial machine vision. In fact, in the early days of Eigen, some of these challenges were really getting in the way of driving value to customers. The good news is, because we're not alone in facing these challenges, there's a lot of really great work that's happening in the industry that's unlocking some value to overcome these. And we believe that because of the innovation that's happening, you're now going to be in a position where before, historically, the effort of deploying a deep learning solution simply didn't warrant the return. We believe that's in the midst of changing. And I think we just saw in the presentation prior to this that the mainstream adoption will start to kick in the next 5 to 10 years. We're certainly witnessing it with our clients. And I will walk you through kind of how we're leveraging tools to be able to drive that adoption at a faster pace. One thing that I will note, Eigen is not a company that believes that deep learning is going to replace rules-based vision. In fact, we believe the two can help each other. And in some cases, rules-based vision solutions still have a place where they can easily solve the problem. We, from our experience, find that there's a place for AI within vision in factories along with the rules-based systems, and AI can actually unlock value that you may not have received prior to deploying the rules-based systems. And I'll talk a bit about what we mean by that here in the subsequent slides. I would say the biggest advancement we've experienced as a company in the deployments we have with our customers, which span across both discrete manufacturing and continuous manufacturing, is our overall time to deploy, or what we like to call time to value. This is really important. We all know that our customers need to be able to go fast. They don't want to be in pilot purgatory for months, if not years. I would say when I started at Eigen 5 years ago, initial deployments for trials or proof of concepts would take months. In some of the complex applications, up to a year to see value. Then when we got to a place where the client wanted to scale the solution, it would be months again to achieve desired outcomes on the subsequent machines and lines. Thankfully for us, things have progressed significantly since then. This is a lot to do with what we're able to do both at the edge and in the cloud. And what you see here on the chart is really on average what we're able to deliver, which is taking the time to do the initial trial back down to within 6 to 8 weeks, demonstrating that AI can actually solve the problem. And then because of some novel techniques that we've deployed on image processing at the edge, we're getting that second instance, that second line, second machine, literally locked in within a day. And I'll talk a bit about how we're able to accomplish that here coming up. One of the things that really helped us accelerate the process of deploying AI or deep learning applications was at the very beginning, where we looked at opportunities to help us accelerate the early stage process of designing the system. As you folks all know, even if it's rules-based or deep learning, the design of any vision system requires a lot of effort, time, and expertise. Testing the sensors, the lighting, applying pre-processing, post-processing, investigating any kind of performance expectations, making sure that the deployment is going to achieve the objectives of the client. We found that simulating the vision solution prior to installation helped us accelerate this process. And not just do that, increase the overall confidence in the system, both our confidence and our clients' confidence. It also gave us a way to minimize the overall costs of hardware that we required to be able to meet the objectives. So what you're looking at here on the screen is Vision Twin. We use this tool to simulate the vision solution prior to installation for all of our projects. Basically, what you do is you import your CAD data, both the machine and the product to be inspected. And then you work through a workflow to define which part of the product must be inspected. Vision Twin then uses AI to calculate the types and numbers of cameras required, and then documents their deployment specifications. So gives you the exact positioning of those cameras based on the inspection coverage that is optimal for your solution. This digital blueprint is designed to maximize the performance of our vision solutions. It really helps us kind of, what you see on the slide, standardize the vision system. And so when you go to move to the next line or the next machine, you now have this digital blueprint that even if the hardware changes or requirements change, the inspection quality remains consistent. So quantity of pixels across the surface, the angles of incidence within limits, all of this becomes a consistent attribute or specification that our clients use to scale. Once the hardware is installed, we also needed to figure out how to minimize overall model training. So this was discussed in the earlier presentation, and a consistent challenge that everyone has in developing an annotated data set that the model can train on. We are not any different than you folks. Sorry, just gonna play the video here. Machine learning requires a substantial data set, and it needs as many potential situations as possible. So for us in quality inspection, this includes possible defects of a product, scratches, stains, bumps, dents. In manufacturing, as you know, that annotated training data is not always readily available. It could be because the product is in limited production, or the time required to annotate the data is just too complex or costly. Our customers just don't have the time. In other cases, the quantity of defects in a data set is extremely limited. So resolving this requires either extended training periods or unexpected costs and scrap through forced defects. We also have looked at the creation of synthetic data, which is also helpful to increase the data sets to improve model performance. But to accelerate this process, what you're looking at here on the slide is we developed software to merge and standardize the images we collected. So in the process that we just reviewed, you're looking at a prototype of one of our applications within automotive. I'll just play it here again. And you're seeing the part go through the conveyor. This is just a prototype. It's designed to perform complex surface inspection on discrete parts. You can see the part moving through the conveyor, and then there are 3 cameras collecting images in real time. Instead of training models on the 3 separate images, we merge the 3 image captures and create a 3D asset of the part that you can see at the end of the video here. We then use this 3D image to annotate defects. And this becomes a virtual perspective that we can leverage across machines because it's standardized that data. I'll show you another view of this so it's clear what I'm talking about. So this is how we merge and standardize the image data. The software is basically taking the 3 raw images that you saw in the previous slide and defining a standard view of the part to be inspected. And this standard view is processed at the edge, so it's not happening in the cloud, it's sitting on an edge device. And what it's designed to do is handle the unexpected variation or process drift that results in changing features in the images over time, like changes in position and orientation of the object in the image. This is what gets scary for people to trust AI, because if things are changing too much, how do they know that the AI is going to know that there's been a drift? A lot of this happens because the part isn't properly nested or the camera perspective changes. And what this tool, Image Twin, does is it converts the data to a sensor agnostic representation that removes undesirable variations such as object position and orientation. This helps us scale the solution between lines. It also reduces data set requirements for new deployments. So instead of developing a dedicated algorithm for each instance, one model can be deployed across all lines and factories. And that's how we got to, when we talked about in the earlier slides, that half-day deployment on the second instance, because you're using the original model from your POC or trial to extend itself into the subsequent lines. Image Twin ensures all machines can also continue to learn from new data collected. So you're not creating a continuous learning system that's localized. You've now expanded it across all the lines that are doing similar parts. And then that unlocks some pretty significant value for our customers to be able to learn common features across machines and lines, regardless of the varying angles and perspectives. Once we had solved for the challenges of designing and deploying the solution, we then looked for opportunities to make the ongoing management of the system easier and also maximize the ROI. So this had us really investing in cloud edge platforms. Traditionally, cloud computing has not been used in machine vision applications. We all know that the reason for this is inference has to happen at the edge, and it wasn't always possible to be able to deliver that kind of inspection in real time in the cloud. Although the real-time requirements of manufacturers continue to require inference at the edge, thanks to the edge computing technologies combined with multi-tenant cloud infrastructure, our clients, ourselves, are now training models in the cloud using the standardized image data. You can see what's happening on the user flow here, and then deploying those models back into the edge across all applicable instances. In some cases, our customers are managing the models themselves. In other cases, we're doing it on their behalf. It really is all about the level of maturity of if they're ready to go there or not. And we found the combination of the cloud edge hybrid model really unlocks the scale piece for our customers, because now they get to manage their vision systems across their enterprise. One just final note on hybrid cloud edge systems. We also unlocked really great value for traditional machine vision solutions using cloud edge, not just traditional, but also the deep learning solutions. You'll see here, seem to be having technical difficulty in my video. what we do with the data in the cloud is correlate the standardized image data with machine process data. And what this is doing is giving users insights into what could be causing the problem to begin with. So what's changing in the process to cause quality issues? You can see in the video, we're capturing both thermal images and optical images, and we're creating a 3D asset of every single inspected part overlaid with critical process data in the cloud. All of this data becomes available across your lines and factories up and down the line. So if your process changes in one part of the process, the software can effectively predict if there will be a problem down the line. And what this enables you to do is work with folks to curate insights that empower and augment the operator to perform actions that drive process improvement, not just yank a part off a line because a defect has been flagged. We found cloud edge machine vision platforms can offer tremendous value for both traditional and rules-based vision solutions, along with deep learning vision solutions. And in fact, some of our clients have asked to have both living within the platform to be able to have almost two inputs of data on anomalies in the process. So to close off, training and deploying deep learning models in industrial machine vision applications can be challenging. We all know that. I think at Eigen, we feel that there's all kinds of reasons to be excited about what's about to come because of the innovations that have taken place on being able to standardize the vision solutions, standardize the image data, and then, of course, as I mentioned, leverage the cloud edge infrastructure. I think for us, we like to talk about it as the voice of the process. Machine vision becomes so much more than defect detection. It's now unlocking a whole continuous improvement learning cycle, which gives manufacturers, vision practitioners, unlimited possibilities for value at scale. If you'd like to learn more about this approach, feel free to download our white paper you see on the slide or reach out to us at any time at eigen.io. And I'm happy to answer any questions you folks have.
Thank you, Erin. We already have a question. Do I have to buy all of your software modules, or is it possible just to buy a single one?
It's a great question. Actually, we are offering the suite dependent on what you need. So you don't need to buy all of the software products all together. We're really designing the offering to make sure that we're targeting the gaps that you may have in deploying systems. So if you need Vision Twin, you can purchase Vision Twin on its own. If you're looking to standardize your image data, that's also an opportunity to integrate into the systems that you're developing. We're trying to be as flexible as possible because we know in some cases you folks have solved some of the other problems that we haven't. So hopefully that answers that question.
Okay, another question. Is deep learning as reliable as rule-based algorithms for industrial quality inspection?
In most cases, yes. So like I mentioned, you really need an annotated training data set, and that data set needs to be sufficient. The main benefit with deep learning is the solution can continually improve when new issues are discovered. So whereas rules-based algorithms are highly customized to specific issues, you really are unlocking a continuous improvement cycle with AI. The key is to make sure your data set is sufficient starting out. And we always like to talk about, it all starts with really good image data collection. If you put a check in the box on making sure you're getting consistent image data, you should be able to annotate the data set.
Okay, thank you, Erin.